So, hello guys. Today we're gonna see the buck converter. Basically, gonna learn about the basics about the buck converters and how it's used in the circuit design or hardware design in electronics. Let's go like first a little bit intro about the basic design architecture of the buck converter. What's inside it? So basically, what we have is a source. It can be battery. It can be it can be a supercapacitor or any DC source. You can have it here. So then after that, what we have basically a switch. So this switch is, this is the responsible uh, you know for the main uh, switching action in the like buck converter. So basically this will turn on and turn off depending upon the frequency of operation and the PWM pulse. So basically what we will do, we give a pulse here to turn on and turn off. So this is like T on and this is T off. Depending upon that, like the source will be connected to the this output cap across the load. So load is connected across the output cap, and then if it off, then when turn off. So basically the whatever the the energy, that current is flowing in this inductor basically. So it will continue to flow because of the there is a energy buildup in the magnetic field. So this inductor stores uh, energy in the magnetic field. When this turns off, the energy stored in the inductor, uh, you know half Li square, so will be delivered to the this output cap, and hence this it will be conducted through this diode, and it will keep circling back into the load and the capacitor output. So this is how, like, the energy is delivered from the source to the load. So first it connects. When the switch turn on, the source is connected to the input source. Load is connected to the input source, and then we have then when the switch turns off, then we and that this inductor energy get transferred into the load, and basically there is no energy coming from the source. So it delivers energy, like in moments. So basically the load never sees the output voltage never reaches the source voltage. So output voltage is always less than the source voltage. That's why we call it the buck converter. And as you already know from the theory, we know the transfer function of this buck converter is VO is divided by V in. Vs basically is equals to the duty cycle. Basically the D is nothing. Duty cycle of this switching of this MOSFET is nothing but dt on divided by total time period. Total time period is nothing, is T on plus T off. Whatever this T we are calling it, this is the time period of this waveform, this square pulse PWM. Okay, so let's go and I'll show you the like how it's used in the practical application. How can we convert, like if we have the 12-volt here in our circuit design or hardware design, so we can convert this 12-volt to suppose say 5-volt, or I can convert this I 5 volt, I can convert it to 3.3 volt or 1.8 volt, whatever whatever my system needs, whatever the like multiple, we have multiple micro processor or controllers that need smaller voltage, so from a higher voltage, so we can convert that accordingly. So I will show you the example how it's used in how used in practical application. So let's go. I'll show you the image. uh, just a second. File. I'll show you here. Where's the image on file? So this is the image we have. Um, just a second. So uh, let's go. So as you can see in the image, right? Oh, it's duplicated. Just a second. So if you can see, basically what's there is like we have the 4 volt system voltage, and this is the integrated buck controller, buck IC. So it has whatever I was showing, like all this thing, this MOSFET, this switch, this, let's call this switch, uh, this switch, and this diode, you know, is integrated into the one IC, and this all control, PWM control, and the feedback from the output voltage is all on the same IC, on the same package. So, and all we have to do is we have to just put an inductor, capacitor, and the some input caps, filtering caps. We have to put. That's all, and our buck converter is ready for our design. So let's see. So what's there is that it is a 4 volt system voltage. So and our controllers need like this various kind of voltage, as you can see. We need 1.1 volt, 1.8 volt, 3.3 volt. Okay, and this is a like high efficiency 1.2 amp synchronous step down converter. So basically in synchronous, like one thing I also wanted to tell you guys is that synchronous is basically we remove this diode. So this diode has a like power dissipation, like if we call PD is equal to VF into forward current, basically, forward voltage into forward current. So this is quite high, like during the discharge of this inductor. So the losses will be quite high. So reduce this conduction losses, we just put, we replicate MOSFET uh, here, like we use MOSFET instead of diode. So that reduces the switching, sorry, conduction loss. So that we know like MOSFET has a very low conduction losses compared to diode. That's why that's known as synchronous buck converter. Basically, we replace the diode with the MOSFET, and it comes with its own PWM control. So that's all on one IC. So let's now see this IC here. So this is the input pin, input voltage pin. This is enable pin. Basically, if I make it high, uh, so if enable pin, what does it do? Like if I turn on this, so it will turn on the this IC. So I will get my system will give the instruction to this IC to turn on. It will give a high pulse, and it will turn on. Then it will convert this whatever the 4 volt is there according to the whatever the feedback I have set. So this feedback decides basically like what will be my output voltage. So my output voltage is proportional to the feedback voltage, basically. So VFP and some K. So that K is that K is decided by this value of this resistor divider, you can see here. So we set this K, and this is fixed for ICs, sometimes zero point 0.6, zero point 0.4, zero point 0.5, something like that. So I set this K, and so I will get the whatever desired output voltage here. So actually, it's not proportional. Now it's almost equal. So this is the like equation. If you see, it's actually is VFP into K. So I'll set the K according to this my requirement of the output voltage through this resistor divider, and I will get the required. So 1.1 uh, 1.1 volt is there at a 1 amp if resistor is 100 and 120.